Have you ever looked up at the night sky and felt that tug of curiosity? The kind that makes you wonder just how far it all goes. The stars we see are only the beginning, tiny pinpricks of light in a cosmic ocean so vast, it defies comprehension. But here's the thing, even the most distant galaxies we've mapped, the ones billions of light years away, are just the opening act. Beyond them lies a frontier so mysterious, so uncharted, that it pushes the very limits of what we think we know about the universe. This is the edge of the observable cosmos, a place where light itself struggles to reach us, and where the rules of reality seem to bend. What is out there beyond the last galaxy? Is there an endless sea of darkness, or could there be structures so colossal, so alien, that they rewrite the textbooks? Scientists call this the cosmic horizon, the final boundary of what we can see, not because there's nothing beyond it, but because the light from those regions hasn't had time to reach us yet. Think of it like standing on the shore of an infinite ocean, watching the waves roll in, but knowing that somewhere beyond the horizon, there are currents and depths we can't even imagine. The universe might be far bigger, far stranger than we've ever dared to guess, and that's exactly what we're diving into today. From the mind-bending theories of multiverses to the eerie silence of the cosmic void, we're embarking on a journey to the farthest reaches of existence. Along the way, we'll explore how astronomers map the unseeable, why the speed of light is both a guide and a barrier, and what clues the earliest moments of the Big Bang might hold about what's lurking in the shadows beyond. This isn't just about science, it's about the human drive to explore, to push past the known and confront the great unknown. So let's take a deep breath and step into the abyss together. The universe has been keeping secrets for 13.8 billion years, and it's time to uncover them. To understand the true scale of the observable universe, picture this: every star, every galaxy, every speck of light we can detect exists within a sphere stretching 93 billion light-years across. But here's the twist: that number isn't just about distance. It's a story of time, light, and the stretching fabric of space itself. Think of the universe like a loaf of raisin bread expanding in the oven. As the dough rises, the raisins' galaxies in this case move farther apart. Now imagine some raisins are moving away so fast that their light can never reach us. That's our cosmic horizon, the ultimate limit to what we can observe. The cosmic microwave background, that faint glow from the infancy of the universe, is our oldest postcard from the edge. It's the afterglow of the Big Bang, captured when the universe was just 380,000 years old. But beyond that, darkness. Not because there's nothing there, but because the universe has been expanding faster than light can travel across it. It's like trying to hear a song played on a radio drifting away from you at the speed of sound. The music exists, but you'll never catch it, and here's where things get even stranger. The expansion isn't just happening, it's accelerating. Galaxies at the very edge of our observable bubble aren't just receding, they're vanishing from view, their light stretched into oblivion by the relentless push of dark energy. One day, far in the future, civilizations might look up and see only their local cluster of galaxies, the rest erased from their sky forever. So when we talk about the observable universe, we're really talking about a window, one that's slowly closing. But that window still gives us clues. The patterns in the cosmic microwave background, the way galaxies cluster together, even the faint whispers of gravitational waves, they're all pieces of a puzzle that hints at what might lie beyond. The universe is under no obligation to make sense to us, yet here we are, mapping the edges of the knowable, one photon at a time. That moment when a ship slips below the ocean's horizon, vanishing not because it ceased to exist, but because the curve of the Earth hides it from view is eerily similar to what happens to galaxies at the edge of our observable universe. Except here, it's not the planet's curvature doing the hiding. It's the expansion of space itself, stretching the fabric of reality so dramatically that light from those distant galaxies can no longer bridge the gap to reach us. This is the cosmic horizon, the final boundary of human observation, where the universe quite literally fades to black. But here's what keeps cosmologists awake at night. Does space simply stop there? Or does it stretch on infinitely, packed with galaxies we'll never see, their light forever lost to the relentless expansion? The truth is, we don't know. Some theories suggest the universe might be finite but unbounded, like the surface of a balloon, where traveling far enough in one direction could theoretically bring you back where you started. Others argue for an infinite cosmos, where every horizon we reach only reveals more horizons beyond. What's certain is that the cosmic horizon isn't just a geographical limit, it's a time capsule. The light arriving from galaxies near this edge set out when the universe was younger, hotter, and denser. By studying them, we're effectively looking backward through cosmic history, glimpsing the universe's adolescence. But beyond that, it's like staring at a blank page in the middle of a thrilling novel. The story might continue, but we're missing the chapters. And then there's the unsettling role of dark energy, the mysterious force accelerating the universe's expansion. It's not just pushing galaxies away, it's erasing them from our future view like a cosmic tide washing footprints from a beach. One by one, galaxies will cross the horizon, their light stretched into undetectable infrared whispers, then silence. Given enough time, the universe visible to any observer will shrink, isolating civilizations in islands of stars surrounded by an ever-growing void. Yet this horizon isn't just a barrier, it's a puzzle box. The way galaxies fade at the edge, the subtle patterns in the cosmic microwave background, even the way space itself warps around massive structures, they're all clues hinting at what might lie beyond. Some theorists speculate about parallel universes bubbling in the unseen depths. Others wonder if the laws of physics themselves change past that invisible line. The cosmic horizon isn't just where light runs out, it's where our imagination fires up. Dark energy isn't just some abstract concept tucked away in a physicist's notebook, it's the silent architect of the universe's fate. An invisible hand stretching the cosmos apart at an ever-increasing speed. Picture a rubber band being pulled from both ends, except instead of snapping back, it keeps stretching forever. That's dark energy in action, and it makes up nearly 70% of everything in existence. Yet, here's the cosmic irony. We can measure its effects, but we have no idea what it actually is. One of the most unsettling theories about dark energy is the Big Rip, a scenario where this relentless expansion doesn't just push galaxies apart, but eventually tears everything apart. First, galaxies would vanish over the horizon, then stars within them would drift into isolation, and finally, even atoms themselves could be ripped to shreds. It's a chilling thought, but it's not the only possibility. Some researchers think dark energy might be a sign of something even stranger. Hidden dimensions, realms of reality folded into the fabric of space-time that we can't perceive. Imagine our universe as a sheet of paper and dark energy as a faint breeze from another sheet just millimeters away, close enough to affect us but forever out of reach. Then there's the puzzle of why dark energy's strength seems perfectly tuned to allow galaxies, stars, and life to exist. If it were slightly stronger, the universe would have expanded too quickly for matter to clump together. Slightly weaker, and gravity might have caused everything to collapse back in on itself long ago. This Goldilocks balance has led some to wonder if dark energy isn't just a random force but a clue to a deeper layer of cosmic design, or even evidence of multiple universes, each with their own laws of physics. What's clear is that dark energy isn't just reshaping our universe, it's reshaping our questions. Every galaxy it pushes beyond our view is a reminder of how much lies hidden, how much we've yet to understand. And as the cosmos accelerates into darkness, one thing becomes certain: the farther we look, the more we realize how little we know. The cosmic microwave background isn't just a faint whisper from the dawn of time. It's a treasure map, etched with secrets about the universe's birth and perhaps even what lies beyond it. Picture this, a glow so ancient, it's been traveling for 13.8 billion years, carrying imprints of the universe's very first moments. But hidden within that static-like haze are tiny ripples, fluctuations in temperature no larger than 1 part in 100,000. To the untrained eye, they might seem like cosmic noise, but to scientists, they're fingerprints of the universe's infancy, clues to how galaxies, stars, and even the cosmic web itself came to be. What makes these ripples even more fascinating is what they might reveal about the unseeable. Some researchers have spotted strange anomalies in the CMB regions where the temperature variations don't quite match the expected patterns. One of the most tantalizing theories is that these oddities could be cosmic bruises, evidence of our universe brushing up against another bubble in a vast multiverse. Imagine blowing soap bubbles in a sink, each one a self-contained universe, its physics slightly different from its neighbors. If two bubbles collided long ago, the shockwave might have left a mark in our CMB, a faint scar from a reality beyond our own. Of course, not everyone's convinced. Skeptics argue these anomalies could just be statistical flukes or artifacts of how we process the data, but the idea is too compelling to ignore. If true, it would mean our universe isn't just one lonely island of reality, but part of an endless froth of universes, each with its own laws, its own history, its own version of existence. Some might be barren, devoid of stars. Others could harbor life in forms we can't even conceive. And if collisions between universes are possible, who's to say there aren't others out there, their echoes lingering just beyond our perception? The CMB is more than a relic, it's a conversation, a dialogue between the universe's first moments and our insatiable curiosity. Every anomaly, every deviation from the expected, is a question waiting to be answered. And as we refine our tools, from next-generation space telescopes to ultra-sensitive detectors, we're not just listening to the past, we're straining to hear the whispers of realities that might lie just beyond the edge of our own. In the first sliver of a second after the Big Bang, something extraordinary happened. The universe didn't just expand, it exploded outward at a speed that defies logic. We're not talking about a gentle stretching of space. This was inflation, a runaway expansion so rapid that a region smaller than an atom ballooned to the size of a galaxy cluster in less time than it takes light to cross a single proton. To put that in perspective, imagine blowing up a grape to the size of the entire solar system in a fraction of a blink. And here's the kicker: space itself was stretching faster than light could travel through it. This isn't science fiction. Inflation is our best explanation for why the universe looks so remarkably uniform in every direction. Without it, we'd expect wildly different temperatures and densities across the cosmos, yet the cosmic microwave background reveals a startling smoothness, like perfectly mixed batter. Inflation stretched those initial wrinkles flat, ironing out the universe's early chaos. But this theory doesn't just solve mysteries, it creates them. Because if space can inflate once, what's stopping it from happening again and again? That's where things get surreal. Some regions of space may have stopped inflating early, becoming the galaxies and stars we see today. But others could still be inflating right now, stretching indefinitely into their own separate universes. each with its own unique physics, its own version of reality. Picture a cosmic foam where every bubble is a self-contained universe, some with stronger gravity, others with no stars at all. Our entire observable cosmos might just be one tiny bubble in an infinite multiverse, forever cut off from neighbors by the relentless expansion of space. The wildest part, we may never know for sure. These other pocket universes, if they exist, lie beyond our cosmic horizon, their light forever too distant to reach us. But inflation leaves behind subtle clues, gravitational waves from the Big Bang's aftermath, or strange patterns in the CMB that could hint at this larger reality. It's like finding footprints on a beach and realizing they lead to an ocean we can't see. Inflation doesn't just rewrite the story of our universe's birth. It suggests we're living in a cosmic neighborhood where the rules might change just over the horizon, where whole other realities could be unfolding in ways we can't even imagine. And if that's true, then the biggest question isn't just what lies beyond the last galaxy, but how many versions of beyond might be out there. What if our universe isn't the only one, not just in the sense of distant galaxies, but as one of countless realities, each with its own unique rules, its own version of physics, even its own history? This is the multiverse hypothesis, an idea that blurs the line between science and the stuff of wild imagination. But here's the twist, it's not just a thought experiment. Serious scientists are exploring versions of this theory, and the math behind it is anything but fiction. Take the concept of bubble universes. Picture a pot of boiling water, with bubbles constantly forming, rising, and popping. Now imagine each bubble is an entire universe born from the same cosmic foam, but sealed off from the others by the sheer speed of inflation. In some of these bubbles, gravity might be stronger, making stars burn out faster. In others, the fundamental constants could be so different that matter never clumps into galaxies at all. Our universe, with its perfect balance for life, might just be one lucky roll of the cosmic dice. Then there's the even wilder idea of parallel realities, alternate versions of our own universe where every possible outcome plays out. Did you take a left turn this morning instead of a right? Somewhere, a version of you did, and that split second spawned a new timeline. This isn't just philosophy, it's a fringe interpretation of quantum mechanics, where every decision branches reality into infinite paths. But how could we ever prove any of this? The answer lies in the shadows of our own cosmos. If another universe brushed against ours long ago, it might have left a faint imprint in the cosmic microwave background, a strange pattern like a bruise from a collision we can't see. Some researchers claim to have spotted these anomalies, though the evidence is still hotly debated. Other clues might come from gravity itself. If extra dimensions exist, as some multiverse theories suggest, they could subtly alter how gravity behaves on the smallest scales. The most mind-bending part, if the multiverse is real, then the question isn't just what lies beyond our last galaxy, it's which version of reality lies beyond it. An infinite tapestry of universes means there could be places where black holes don't evaporate, where time runs backward, or where life takes forms we can't even comprehend. And yet, we're forever trapped in our own bubble, limited by the speed of light and the expansion of space, left to wonder if we're alone in the cosmos or just one note in an infinite symphony. This isn't just about satisfying curiosity. The multiverse hypothesis forces us to confront the deepest questions of existence. Are the laws of physics fine-tuned for life, or are we simply living in the one universe where they happen to align? Is our reality special, or is it as common as sand on a beach? Every time we push the boundaries of what we know, the universe seems to push back, revealing new layers of mystery. And if the multiverse is real, then the greatest frontier isn't beyond the last galaxy, it's beyond the very fabric of reality itself. At the quantum level, reality behaves in ways that seem almost magical. Particles wink into existence and vanish again, borrowing energy from the vacuum of space itself. These fleeting bursts of matter and antimatter, known as quantum fluctuations, aren't just microscopic oddities. They might be the hidden architects of entire universes. Imagine a cosmic version of a soap bubble splitting in midair, where each tiny droplet becomes its own self-contained world. That's the startling possibility some physicists are exploring, that every quantum fluctuation could, under the right conditions, inflate into a full-fledged universe, complete with its own laws of physics. The math behind this idea stems from a marriage of quantum mechanics and general relativity. When a fluctuation occurs in the fabric of space-time, it could theoretically trigger a runaway expansion, a mini-inflation event, birthing a pocket universe disconnected from our own. These baby universes might pinch off like buds on a cosmic vine, forever hidden from us beyond the veil of space-time. It's a concept that turns the edge of our observable universe into something far more dynamic than a mere boundary. Instead, it could be a seething frontier where new realities constantly bud and drift away like embers floating into the night. But how would we ever detect such a thing? One clue might lie in the gravitational echoes of these events. If a baby universe formed near the edge of our own, its birth could have sent ripples through the fabric of space-time, gravitational waves subtle enough to evade current detectors but potentially observable with future technology. Another tantalizing hint could come from anomalies in the cosmic microwave background, where the energy of a budding universe might have left a faint fingerprint. The implications are staggering. If this theory holds, our universe might not just be one among many in a static multiverse. It could be part of an ever-growing family tree, with new universes branching off constantly. Some might resemble ours with stars and galaxies. Others could be wildly different, their physics so alien that matter as we know it never forms. And here's the real mind bender. If our own universe began as a quantum fluctuation in some larger meta-reality, then the cycle could be eternal, with universes giving birth to universes in an unending cosmic dance. This isn't just speculative physics, it's a radical reimagining of existence itself. The idea that emptiness could spontaneously generate reality challenges our deepest intuitions about cause and effect. Yet at the quantum scale, nothing is never truly empty. It's a seething ocean of potential where particles flicker in and out of being, and where the seeds of new universes might lie hidden in the fabric of the void. The edge of our cosmos isn't just a horizon, it could be a threshold with infinite new worlds waiting on the other side. Black holes aren't just cosmic vacuum cleaners, relentlessly devouring everything in their path. They're the universe's most extreme laboratories, where the laws of physics as we know them break down entirely. At the edge of a black hole, time slows to a crawl, space twists like taffy, and gravity becomes so overpowering that not even light can escape its grip. But what happens beyond that point of no return, the event horizon? Some theories suggest these celestial monsters might not be dead ends at all, but tunnels, gateways to realms so bizarre, they make the farthest galaxies seem ordinary by comparison. Take wormholes, for example. Einstein's equations hinted that black holes could theoretically connect to white holes, the opposite of black holes, spewing out matter instead of trapping it. If these two extremes were linked, they'd form a bridge through space-time, a shortcut across the cosmos, or even to another universe entirely. Picture folding a piece of paper so two distant dots touch. A wormhole would be the pen stroke connecting them, bypassing the long journey in between. The catch: no one knows if wormholes are stable enough to survive. or whether the tidal forces inside a black hole would shred anything or anyone attempting the trip. Then there's the even wilder idea that black holes might be cosmic birthing chambers for new universes. Inside a black hole's crushing core, matter doesn't just vanish, it's compressed into an infinitely dense point called a singularity. Some physicists speculate that this singularity could trigger a new Big Bang, spawning an entirely separate universe with its own laws of physics, hidden forever behind the veil of the event horizon. In this scenario, our own universe might have been born this way, the child of a black hole in some larger, unknowable cosmos. Of course, these ideas are still firmly in the realm of theory. We can't peer inside a black hole, no information escapes, no signals get out, but that hasn't stopped scientists from hunting for clues. The way black holes bend light around them, the gravitational waves they send rippling through space-time when they collide, even the faint glow of Hawking radiation at their edges. All of these are breadcrumbs leading us closer to understanding what might lie within. And here's the most tantalizing thought. If black holes do lead somewhere, they might be our only shot at answering what's beyond the observable universe. While galaxies at the cosmic horizon fade from view, black holes offer a different kind of frontier, one where the limits aren't just about distance, but about the very fabric of reality itself. They're cosmic riddles, daring us to imagine what lies past the point where physics as we know it ends. Whether they're portals, destroyers, or creators, one thing's certain: black holes are the universe's way of reminding us that the unknown isn't just far away. It might be hiding in plain sight, in the darkest corners of the sky. String theory doesn't just tweak our understanding of reality, it shatters it. Imagine living in a world where you could only perceive two dimensions, like a character trapped on the surface of a piece of paper. To you, a three-dimensional object like a sphere passing through your flat world would appear as a dot that grows into a circle, then shrinks back to nothing. That's how limited our view of the cosmos might be. According to string theory, the three dimensions we experience, length, width, and height, could be just the visible fraction of an 11-dimensional universe, with the rest curled up into spaces so tiny they're hidden from even our most powerful microscopes. This isn't just a mathematical curiosity. If higher dimensions exist, the galaxies we observe might not be standalone objects, but shadows, projections of vast, multidimensional structures we can't fully perceive. Picture holding up a cardboard cutout to a flashlight. The shadow it casts on the wall is a flat, simplified version of the real thing. Now imagine that cutout is a galaxy, and the real thing is a higher dimensional shape moving through realms we can't access. The implications are staggering. Dark matter, that mysterious substance making up most of the universe's mass, could simply be ordinary matter bleeding into our dimension from these hidden layers. Even gravity's puzzling weakness compared to other forces might be explained if it's leaking into other dimensions, diluting its strength in our own. But how could we ever test such a mind-bending idea? One clue might come from particle colliders. If higher dimensions exist, smashing particles together at extreme energies could create tiny, fleeting vibrations, evidence of strings looping through unseen dimensions. Another hint could lie in the fabric of space-time itself. Just as a two-dimensional creature couldn't grasp the concept of up, we might be missing subtle warps or ripples in higher dimensions that distort gravity in ways we've yet to detect. The most radical possibility, our entire observable universe might be a brane, a three-dimensional membrane floating in a higher dimensional bulk. Other branes could exist parallel to ours, each hosting their own universes with different physical laws. Collisions between these branes might even trigger events like the Big Bang, resetting cosmic history over and over. It's a vision that turns beyond the last galaxy into something far stranger, not just distant space, but adjacent dimensions, separated by less than the width of an atom, yet utterly unreachable. String theory is still unproven, and critics argue it's more philosophy than science. But if it's correct, the frontier of the cosmos isn't just about distance, it's about peeling back layers of reality we never knew existed. The galaxies we see, the voids we map, even the laws of physics we take for granted could be whispers of a deeper, richer universe, one where beyond isn't a direction, it's a dimension. What if everything around us, every star, galaxy, even the vast emptiness between them isn't what it seems? The holographic principle turns our understanding of reality inside out, suggesting that the three-dimensional universe we experience might be nothing more than a projection, like a movie playing on the surface of an invisible screen. Imagine standing in front of a massive waterfall, feeling the mist on your face, hearing the roar, but then discovering it's all an illusion, a high-tech hologram with no actual water. That's the level of cosmic sleight of hand some physicists are proposing. According to this mind-bending idea, all the information needed to describe our universe, every particle, every force, even time itself, could be encoded on a two-dimensional boundary at the edge of space, like a cosmic DVD storing the data for an immersive 3D experience. The math behind this isn't science fiction. It emerged from studying black holes, where scientists realized the information swallowed by these gravitational monsters isn't lost but smeared across their event horizons, like a message written in vanishing ink on a spherical surface. If a black hole's contents can be stored on its surface, why not the entire universe? This line of thinking led to a staggering possibility. What we call space might just be a holographic reconstruction, a trick of the light played by reality itself. The galaxies at the edge of our observable universe wouldn't be physical objects in the traditional sense, they'd be pixels in a cosmic display, their light and motion dictated by data etched onto a distant, unseen wall. But here's where it gets even stranger. If the holographic principle is correct, then the question, what lies beyond the last galaxy, takes on a whole new meaning. There might not be a beyond in the way we imagine. Instead, the boundary of the universe could be like the edge of a computer screen, the place where the projection stops, but where the real action, the code generating the simulation, resides in a deeper, more fundamental layer. It's as if we've spent centuries staring at shadows on a cave wall, unaware that the true reality exists outside in the light. Critics argue that the holographic principle is untestable, more philosophy than physics. Yet experiments are underway. Powerful lasers and precision instruments are searching for telltale pixelation in the fabric of space-time, tiny, grain-like fluctuations that would betray the universe's hidden 2D nature. Others are probing quantum entanglement, where particles remain mysteriously linked across vast distances, as if their connection exists outside our three-dimensional space. These phenomena could be glitches in the hologram, clues that we're living in a constructed reality. Whether the holographic principle holds up or not, it forces us to confront a humbling truth. The universe might be far weirder than our senses suggest. The edge of the cosmos isn't just a line on a map. It could be the seam between reality and something deeper, a place where the rules we take for granted dissolve into something beyond our comprehension. And if that's true, then the greatest mysteries aren't just out there among the galaxies. They're written in the invisible ink of existence itself, waiting for us to decipher the code. Between the glittering threads of galaxy clusters, where the universe seems to crowd itself together, there are deserts so vast they defy comprehension, cosmic voids, regions of space where galaxies are almost entirely absent. These aren't just small gaps, some stretch hundreds of millions of light years across. making them among the largest structures in existence. To put that in perspective, if our Milky Way were a grain of sand, crossing one of these voids would be like traversing an empty football stadium. And yet, for all their emptiness, these voids might hold some of the universe's most profound secrets. At first glance, a void seems simple, just an absence, a blank spot on the cosmic map. But emptiness in space is never truly empty. Even in these desolate regions, there are still a handful of lone galaxies, drifting like ships in an endless ocean. More intriguingly, there's dark energy, the mysterious force accelerating the universe's expansion. In voids where gravity's pull is weakest, dark energy reigns unchallenged, stretching space faster than anywhere else. Some scientists speculate that voids could be windows into the universe's ultimate fate, places where dark energy's effects are magnified, offering a preview of how all structures might one day be torn apart. Then there's the wilder possibility that voids aren't just empty but different. One radical theory suggests they could be regions where the fabric of spacetime itself is warped, creating bridges to other universes in a vast multiverse. Think of it like bubbles in a block of Swiss cheese. Our universe is the cheese, and the voids might be places where other bubbles press up against ours. If true, these voids wouldn't just be absences, they'd be portals, their apparent emptiness masking a connection to something beyond. But how would we even test such an idea? The answer lies in the subtle clues voids leave behind. The way light bends as it passes through them, the faint echoes of gravitational waves, even the peculiar motions of galaxies at their edges, all of these could hint at something unusual lurking in the darkness. Some researchers are even scanning voids for anomalies in the cosmic microwave background, searching for imprints of collisions with other universes. The most humbling thought, voids might be more than just gaps. They could be the universe's way of balancing itself, the yin to galaxy clusters yang. Without them, matter would clump too densely, stars would burn too brightly, and life might never have had the chance to emerge. In that sense, these vast emptinesses aren't just accidents, they're essential, sculpting the cosmos into the shape we see today. And if we ever hope to understand the full story of the universe, we'll need to venture into these deserts, listening for whispers in the dark. Hundreds of millions of light years from Earth, in the direction of the constellations Centaurus and Hydra, something invisible is bending the motion of galaxies like a cosmic magnet. This is the Great Attractor, a gravitational anomaly so powerful, it's pulling entire galaxies, including our own Milky Way, toward it at over 600 kilometers per second. Yet despite its immense influence, we can't see it directly. Our view is blocked by the dense band of stars and dust in our galaxy's disk, as if the universe has placed a celestial blindfold over our eyes. What makes this mystery even more compelling is the scale of the forces at play. The Great Attractor isn't just tugging on a few nearby galaxies. It's part of a vast flow of motion affecting thousands of galaxies across hundreds of millions of light years. Imagine dropping ink into a swirling drain. The way those tendrils spiral inward is eerily similar to how galaxies are being drawn toward this invisible epicenter. But here's the catch. Based on the visible matter we've mapped in that region, galaxy clusters like Norma and Able 3627, there shouldn't be enough mass to explain such a colossal pull. That missing gravity points to something lurking in the shadows, something we haven't fully accounted for. One leading theory suggests the Great Attractor might be a supercluster of dark matter, an invisible scaffold weaving through space, its gravitational grip far outweighing the galaxies we can see. But some researchers think the truth could be even stranger. The pull might not be coming from a single structure at all, but from something beyond our observable horizon, an unimaginably massive assembly of matter so distant its light hasn't had time to reach us. It's like standing in a valley and feeling a wind you can't see, only to realize later it's being funneled from a storm over the mountains just out of view. Then there's the spine-chilling possibility that the Great Attractor is just the tip of the iceberg. Beyond it lies an even larger gravitational anomaly known as the Shapley supercluster, a sprawling metropolis of galaxies 8 times more massive than the Great Attractor itself. Together, these titans might be part of a cosmic tug-of-war with our local group of galaxies caught in the middle. But here's what keeps astronomers up at night. If structures like these can exist, what else is out there, hidden beyond the limits of our vision? The deeper we probe, the more the Great Attractor challenges our assumptions. It's a reminder that the universe doesn't owe us easy answers, that some of its most profound secrets are written in motions rather than light, in whispers of gravity rather than shouts of radiation. And as we piece together this puzzle, one thing becomes clear. The farther we look, the more we realize how much of the cosmos remains in the shadows, waiting to be discovered. If galaxies were fireflies, their glow wouldn't be scattered randomly through the night. They'd trace out shimmering, interconnected threads, forming a web of light stretching across the cosmos. That's the reality we've uncovered. Galaxies cling together in vast filaments, the largest structures in the universe, weaving a tapestry so immense it makes superclusters look like mere knots in the threads. These filaments, some stretching over 500 million light-years, are the universe's hidden skeleton, a blueprint written in gravity and dark matter. But here's the spine-tingling part. We've only mapped the fragments within our cosmic horizon. What if these filaments don't end where our telescopes lose sight? What if they stretch infinitely, connecting universes beyond our own? The cosmic web isn't just a pretty pattern. It's a record of the universe's earliest moments, when quantum ripples in the newborn cosmos were stretched by inflation into sprawling tendrils of matter. Picture pouring cream into coffee and stirring the swirls you see are a scaled-down echo of how dark matter pooled along these filaments, pulling galaxies into their gravitational embrace. The Milky Way, just one speck on a filament's edge, like a dewdrop clinging to a spider's silk. And just as spider webs tremble when touched, these filaments vibrate with the motion of galaxies, their gravity orchestrating a dance that's lasted billions of years. But the real mystery lies beyond the map's edge. If filaments extend past our observable universe, their structure could hint at something even grander, an infinite web, with our corner just one stitch in a cosmic quilt. Some models suggest these threads might curve back on themselves, wrapping the universe into a shape we can't yet fathom. Others propose they're highways to voids, those deserts of emptiness where dark energy's grip is strongest. And then there's the most radical idea, that filaments could be scars from collisions with other universes, their gravitational echoes frozen in the web's pattern. Mapping these filaments isn't just about filling in blanks. It's about decoding the universe's DNA. By studying how galaxies cluster along these threads, we've uncovered clues about dark matter's ghostly grip and dark energy's relentless push. Future telescopes like the Vera Rubin Observatory will trace these filaments deeper into the void, hunting for galaxies so faint they're barely more than whispers. Each new thread we uncover rewrites our place in the cosmos, not as the center, but as travelers standing where a few strands cross, daring to guess at the loom that wove them. The cosmic web doesn't just connect galaxies, it ties our questions together about where the universe ends, how it began, and whether we're alone in its weave. Every filament is a road, a boundary, and a riddle all at once. And if we ever find its edge, we might discover it wasn't an edge at all, just another curve in the tapestry, leading somewhere even stranger. Light from the edge of our observable universe is already ancient, a time capsule from when the cosmos was just a fraction of its current age. But here's the haunting reality. Every second, that edge recedes farther into the past as the universe expands, pushing galaxies beyond a point where their light can ever reach us. It's as if we're standing on a shoreline, watching the tide pull priceless artifacts into the deep, knowing we'll never retrieve them. Time isn't just a measure of cosmic history. It's an active participant, deciding what parts of reality remain visible to us and what parts vanish forever. The cruel irony is that the universe's expansion doesn't just create distance, it erases evidence. Galaxies drifting beyond our cosmic horizon aren't simply moving away. They're being erased from our future by the relentless stretching of space itself. Their light, still traveling toward us, will eventually hit a wall where space expands faster than light can traverse it. Imagine a runner on a treadmill that keeps speeding up no matter how fast they sprint. They'll never reach the end. For those distant galaxies, their final photons are like that exhausted runner, destined to fade into the void, their stories lost to time. This raises a chilling possibility. If the universe is infinite, there could be entire civilizations, structures, even other big bangs unfolding right now in regions so distant that their light hasn't just not reached us yet, it never will. No telescope, no matter how advanced, could ever glimpse them. The universe might be teeming with wonders, but we're trapped in a bubble of observability, a snow globe shaken by forces we can't control. Yet time's grip isn't absolute. The cosmic microwave background gives us a snapshot of the universe at 380,000 years old, a baby picture frozen in light. But peer further back and the fog of the early cosmos thickens. The first atoms hadn't even formed. Space was a plasma so dense, light couldn't travel freely. To see beyond that wall, we'd need to detect something light can't carry. Primordial gravitational waves, ripples from the universe's violent birth. These waves, if we can ever catch them, would be whispers from the first trillionth of a second, carrying secrets from a time before time had meaning. The most unsettling question isn't whether the universe is infinite, it's whether infinity even matters if we're forever cut off from most of it. We might be like ants in a vast library, surrounded by books we can't open, written in languages we'll never decipher. But here's the twist. Even if we're trapped in our observable bubble, the clues we can gather, the distribution of galaxies, the echoes of the Big Bang, the ghostly pull of dark energy might hint at what lies beyond the veil. Time may be the ultimate prison, but it's also the key. Every second that passes isn't just stealing distant light. It's giving us more data, more context, more tools to pry open the universe's deepest mysteries. Think of the universe's shape like a cosmic origami project folded in ways we can't see, but whose creases dictate everything from the fate of galaxies to whether space itself has an edge. The question isn't just academic, it's about the fundamental architecture of reality. If the universe is flat, parallel laser beams would stay perfectly aligned forever, never converging or diverging. If it's closed like the surface of a balloon, those beams would eventually curve back and meet. And if it's open, they'd drift apart endlessly, like tracks on a saddle stretching into infinity. For decades, scientists have hunted for these cosmic curves. The most telling clues come from the cosmic microwave background, that fossilized glow of the Big Bang. Tiny temperature fluctuations in this ancient light act like a cosmic ruler. If the universe were curved, distant patches would appear larger or smaller than expected, like continents warped on a globe. But the measurements so far reveal something startling. Space appears flat to within a razor-thin margin of error. Not probably flat, a perfectly flat, like a pane of glass extending forever. But here's the catch. Our instruments can only measure so precisely. there's still a slim chance the universe is subtly curved, like a sphere so vast its curvature is invisible to us. If that's true, the implications are mind-bending. A closed universe would mean space isn't infinite, it just feels that way because it loops back on itself. Travel far enough in one direction and you'd end up where you started, like an ant crawling on a basketball. The edge we're searching for wouldn't exist. Instead, beyond the last galaxy might just be the Milky Way seen from another angle, billions of years in the future. An open universe, on the other hand, would be infinite in every sense, no loops, no boundaries, just endless space growing more fractured and empty as dark energy tears galaxies apart. But the flat universe we seem to inhabit is the strangest of all. It suggests a precise balancing act in the Big Bang's aftermath, where matter and energy were distributed with near mathematical perfection. Too much density and the universe would have collapsed inward. Too little and it would have flown apart before galaxies could form. Yet even a flat universe hides mysteries. If it's truly infinite, then somewhere beyond our cosmic horizon, there could be exact copies of you, me, even Earth, not doppelgangers, but statistical inevitabilities in a limitless expanse. Or perhaps the flatness is an illusion, a local quirk of our observable bubble masking a grander shape we can't perceive. The only way to know for sure is to measure the cosmos with even finer precision, hunting for whispers of curvature in the gravitational waves left over from the universe's birth. The shape of the universe isn't just about geometry, it's a mirror reflecting how much we've yet to learn. Every time we think we've mapped reality, the cosmos reminds us that the simplest questions is space finite. Does it loop? Are still wide open, and until we find the answers, the universe's true form remains one of its most tantalizing riddles. Imagine the universe not as an endless expanse, but as a cosmic donut where traveling in a straight line long enough would eventually bring you right back to where you began. This isn't some whimsical thought experiment. It's a serious scientific hypothesis known as compact topology. If true, the idea of an edge to the universe would vanish entirely, replaced by a strange, looping geometry where beyond is just an illusion. The math behind this theory traces back to Einstein's general relativity, where space itself can bend and twist in ways that defy our everyday intuition. Picture an old-school video game where a spaceship flying off the right side of the screen reappears on the left, except in this case, the screen is the entire cosmos. In a donut-shaped universe, light from a distant galaxy could theoretically circle around and hit us from multiple directions, creating ghostly duplicates in the sky. Astronomers have even scanned the cosmic microwave background for these telltale repeating patterns, though so far the evidence remains elusive. But why a donut? Of all possible shapes, this one, technically called a torus, offers a unique blend of simplicity and strangeness. Unlike a spherical universe where space curves uniformly, a torus has regions of varying curvature, like the tight bends near the donut's hole versus the gentler slopes on its outer edge. This could subtly alter how galaxies cluster or how light travels across cosmic distances. Some simulations suggest that if the universe were torus-shaped, vast structures like galaxy filaments might align in unexpected ways, weaving around the hidden geometry like threads on a loom. The implications are dizzying. If the universe loops back on itself, then every direction we look might eventually lead home, not just in space but in time. Light from the Milky Way could have traveled the full circuit of the cosmos, meaning we might someday see our own galaxy as it was billions of years ago, a pale echo of itself embedded in the night sky. Even black holes could take on new roles in this model, their singularities potentially acting as shortcuts through the donut's twisted geometry. critics argue that without direct evidence, compact topology remains a mathematical curiosity. Yet the idea persists because it solves one of cosmology's biggest puzzles: why the universe appears so uniform in every direction. If space is a donut, its looping nature could explain how distant regions had time to communicate their conditions in the early universe, smoothing out irregularities without requiring exotic physics like inflation. It's a radical trade-off, replacing an explosive stretching of space with a hidden twist in its fabric. Whether the universe is a torus or not, the mere possibility forces us to rethink the nature of reality. If beyond the last galaxy isn't a frontier but a loop, then the cosmos isn't just vast, it's ingeniously interconnected, a cosmic Möbius strip where every ending is a beginning in disguise. And that's the real allure of compact topology. It doesn't just map the universe's shape, it challenges us to imagine a reality where even infinity has folds. The silence of the cosmos isn't just puzzling, it's deafening. With hundreds of billions of galaxies, each hosting billions of stars, the universe should be teeming with civilizations. Yet, as physicist Enrico Fermi famously asked, "Where is everybody?" this contradiction, known as the Fermi paradox, cuts to the heart of our cosmic loneliness. If life is common, why does the universe feel so empty? One unsettling possibility is that the very vastness we find so awe-inspiring might be a trap, a cosmic quarantine sealing civilizations off from one another before they can ever meet. Consider the Great Filter theory, the idea that some catastrophic barrier prevents life from progressing beyond a certain point. This filter could lie in our past. Perhaps the emergence of life itself is astronomically rare. Or worse, it might await us in the future, a looming existential threat like self-destructive technology or an unavoidable cosmic disaster. But here's the spine-chilling twist. What if the filter isn't just time, but space? The voids between galaxies, those unimaginably empty deserts, might not just separate us from other civilizations, they might actively erase them. Imagine a universe where expanding space acts like a cosmic shredder, stretching signals from distant worlds into undetectable noise before they ever reach us. Then there's the darker alternative. We're not just isolated, we're hidden. Some theories suggest advanced civilizations might deliberately cloak themselves, avoiding detection to escape predatory neighbors or existential risks. Others propose that the universe's accelerating expansion is a one-way curtain, ensuring no two civilizations ever overlap in time and space long enough to communicate. It's like being stranded on an island in an endless ocean, waving at shores we'll never see, while the tides pull us farther apart every second. But what if the answer isn't in the voids or the silence, but beyond the cosmic horizon? Regions of the universe forever outside our view could harbor civilizations thriving in ways we can't fathom, their light eternally outpaced by the expansion of space. Or perhaps life is a fleeting spark in the grand timeline of the cosmos, blinking in and out of existence like fireflies in the night, never overlapping long enough to find one another. The Fermi paradox doesn't just question whether we're alone. It forces us to confront the terrifying idea that the universe might be designed for solitude, that the same forces which forged galaxies and stars also built walls between them. And if that's true, then the edge of the observable universe isn't just a boundary of light. It's a prison wall, and we're on the inside. In October 2017, astronomers spotted something streaking through our solar system that didn't belong, a reddish, cigar-shaped object moving too fast to be bound by the sun's gravity. Named Oumuamua, Hawaiian for scout or messenger from afar, it was the first confirmed visitor from interstellar space, but this wasn't just any space rock. Its behavior was weird. Unlike comets, it showed no visible tail of gas or dust as it warmed near the sun. Unlike asteroids, its shape was bizarrely elongated, possibly 10 times longer than it was wide. And most puzzling of all, it accelerated slightly as it raced away, as if something were giving it an extra push. Theories exploded. Could Oumuamua be a fragment from a shattered planet, ejected from another star system? Or perhaps a hydrogen iceberg, sublimating invisibly in sunlight and propelling itself forward? Then came the wilder idea: what if it wasn't natural at all? Harvard astronomer Avi Loeb famously suggested Oumuamua might be artificial, a light sail or probe from an alien civilization, its unusual acceleration caused by radiation pressure pushing against a thin, reflective surface. The scientific community largely dismissed this as speculation, but the debate spotlighted a deeper truth. We'd never seen anything like Oumuamua before, and our tools for studying it were frustratingly limited. Here's the kicker: Oumuamua was already racing out of the solar system when we noticed it. By the time telescopes swung into action, the object was too distant to photograph clearly, leaving us with only fragments of data, flickers of light and motion that spawned more questions than answers. It's like catching a glimpse of a stranger sprinting through your backyard at midnight, only for them to vanish into the darkness before you can even grab a flashlight. But Oumuamua's legacy isn't just about what it was, it's about what it represents. If one interstellar visitor slipped through unnoticed until the last moment, how many others might be out there, lurking in the shadows of our solar system? Some estimates suggest there could be thousands of such objects passing through at any given time, each a potential time capsule from distant star systems, carrying clues about how planets form, how materials travel between stars, or even how life might spread across the galaxy. Future telescopes like the Vera Rubin Observatory will scan the skies for more of these cosmic nomads, ready to catch them earlier and study them in detail. The real mystery of Oumuamua isn't just its identity. It's the reminder that the universe is constantly tossing surprises into our backyard, some natural, some perhaps beyond our current understanding. Whether it was a weirdly shaped rock or something far stranger, its fleeting visit challenges us to ask, what else is sailing through the dark, unseen and unexplained? And when the next scout arrives, will we be ready? Fast radio bursts are cosmic enigmas that pack the energy of hundreds of millions of suns into mere milliseconds, blazing flashes of radio waves so powerful they can be detected across billions of light years. Since their discovery in 2007, these fleeting signals have puzzled astronomers with their unpredictability and sheer intensity. Some burst once and vanish without a trace. Others, like the famous FRB 12112, repeat in erratic patterns, flickering like a malfunctioning cosmic lighthouse. What makes these signals even stranger is their origin. They're not coming from our galactic backyard, but from galaxies so distant, their light has traveled for billions of years before reaching us. The leading theories suggest natural explanations: extreme astrophysical events like magnetars, highly magnetized neutron stars that could unleash these bursts as their crusts crack under intense magnetic strain. Picture a spinning neutron star, its surface twisted by forces so strong, they occasionally snap like an overwound rubber band, releasing a shockwave of radio energy. Yet some FRBs defy even these exotic explanations. Their repeating patterns don't quite match known stellar behaviors, and their frequencies sometimes drift in ways that don't align with typical cosmic phenomena. This has led to more speculative ideas. Could some FRBs be artificial beacons or even accidental leakage from advanced civilizations? The notion isn't as far-fetched as it sounds. Human technology already leaks radio signals into space. A sufficiently advanced society might generate bursts detectable across intergalactic distances. Some researchers have even proposed that the precision of certain FRB patterns could hint at engineered rather than natural origins. Imagine a civilization harnessing the power of neutron stars to send messages, or perhaps using FRBs as propulsion beams for light sails, tapping into the universe's most energetic forces to navigate the cosmos. But here's the twist: even if FRBs are purely natural, their existence challenges our understanding of the universe's extremes. They act like cosmic flashlights, illuminating the invisible gas between galaxies as their signals pass through it. By studying how these bursts disperse, scientists have uncovered missing matter, a gas so diffuse it had eluded detection for decades. FRBs might also serve as tools to probe the universe's expansion, their distortions offering clues about dark energy's grip on spacetime. The most tantalizing possibility: some FRBs could originate from beyond our observable universe. If the cosmos is far larger than the 93 billion light-year bubble we can see, their signals might be leaking into our reality from regions forever out of reach. It's like hearing echoes from a room we can't enter, each burst a cryptic postcard from a place we'll never map. Whether natural or artificial, FRBs are more than just cosmic static. They're reminders of how much we don't know. Every flicker from the void forces us to reconsider what's possible, pushing the boundaries of both astrophysics and imagination. And with new telescopes like the Square Kilometre Array coming online, we might soon catch these radio ghosts in the act, decoding their secrets 1 millisecond burst at a time. Gravitational waves are the universe's hidden messengers, ripples in the very fabric of spacetime, born from the most violent collisions imaginable. When black holes spiral into one another or neutron stars tear each other apart, they don't just release light or radiation. They send shockwaves through the cosmic medium itself, warping space like a stone dropped into a pond. These waves, first predicted by Einstein over a century ago, weren't directly detected until 2015, when LIGO, the Laser Interferometer Gravitational Wave Observatory, captured the faint echoes of two black holes merging over 1 billion light-years away. That discovery didn't just confirm a theory, it opened a new window on the cosmos, one where we don't just see the universe, we listen to it. What makes gravitational waves so revolutionary is their ability to reveal what light cannot. Take black holes, for example. These cosmic voids are the ultimate cloaking devices, swallowing everything, even light, that ventures too close. But when they collide, the energy they release doesn't come from their insides. It's written in the distortions of spacetime itself. Gravitational waves carry that story directly to us, bypassing the black holes in Chi darkness. It's like sitting in a pitch-black room and hearing two dancers collide. You might not see them, but the thud tells you everything about their mass, speed, and final embrace. Now, imagine extending that hearing to the very edge of the observable universe and beyond. Current detectors like LIGO and Virgo are sensitive enough to pick up mergers within a few billion light-years, but next-generation observatories, like the planned LISA mission in space, could detect waves from the universe's earliest epochs. Some theorists even speculate that ultra-low-frequency gravitational waves with wavelengths spanning light-years might carry whispers from beyond our cosmic horizon. These wouldn't be from recent collisions, but from events so ancient their light will never reach us. It's as if the universe left voicemails in space-time, recorded billions of years ago, and we're just now finding the playback button. The most tantalizing possibility: gravitational waves might be our only way to probe the multiverse. If other universes exist in a higher dimensional bulk, as some string theory models suggest, their collisions or vibrations could imprint faint ripples in our space-time cosmic echoes from realms we'll never see. Even if those signals are vanishingly weak, future detectors tuned to the right frequencies might catch them, like eavesdropping on a conversation through a shared wall. Of course, not all gravitational wave signals would be so exotic. Some might come from entirely natural but bizarre phenomena, like cosmic strings, hypothetical defects in spacetime left over from the Big Bang, vibrating like snapped guitar strings. Others could be the death throes of primordial black holes, tiny relics from the universe's birth, evaporating in bursts of gravitational energy. Each signal would be a puzzle, a piece of the cosmos's hidden history waiting to be decoded. But here's the catch: gravitational waves aren't just passive signals. They're active participants in the universe's evolution. Supermassive black hole mergers, for instance, can kick their remnants clear out of galaxies, sending them careering through intergalactic space. The waves they produce might even nudge nearby stars or gas clouds, subtly shaping the cosmos over eons. It's a reminder that the universe isn't just something we observe, it's something we're embedded in. A dynamic medium where every collision, every explosion, sends ripples through the shared fabric of reality. The next time you look up at the night sky, remember, the silence is an illusion. Beneath the stillness, spacetime is alive with vibrations, some from yesterday, some from the dawn of time, and some, perhaps, from places we'll never see. Gravitational waves don't just let us explore the universe, they let us feel it. What if everything we perceive as reality, the stars, galaxies, even the laws of physics themselves, is nothing more than an elaborate simulation running on some unfathomable cosmic computer? This isn't the plot of a sci-fi movie. It's a serious hypothesis debated by physicists and philosophers alike. Known as simulation theory, the idea suggests that our universe might be a meticulously crafted digital construct, with beyond the last galaxy simply marking the edge of its rendering capacity. Think of it like a video game where distant objects fade into low-resolution textures because the system can't process infinite detail. Only here, the system is the very fabric of existence. The roots of this theory stretch back further than you might expect. Philosopher Nick Bostrom formalized the modern argument in 2003, positing that at least one of three possibilities must be true. Either advanced civilizations never reach the technological capability to create simulations, they choose not to run them, or we're almost certainly living in one. The logic hinges on probability. If future civilizations can simulate conscious beings, the number of artificial minds would dwarf the number of original ones, making it statistically likely we're among the simulated. Elon Musk and Neil deGrasse Tyson have publicly entertained the idea, with Musk famously stating the odds we're in base reality are 1 in billions. But how would we even test such a radical claim? Some researchers propose looking for glitches in the simulation, tiny errors or shortcuts a programmer might have taken. For instance, high-energy cosmic rays exhibit unexpected behavior at certain energy levels, as if the universe's physics engine hits a processing limit. Others suggest quantum entanglement, where particles instantly influence each other across vast distances. Could be a computational optimization like a game, rendering only what the player observes to save resources. Even the finite resolution of space-time at the Planck scale has been cited as potential evidence. If the universe were a simulation, it would need a pixel size, and Planck length might be it. The implications are staggering. If we're in a simulation, the edge of the observable universe might not be a physical boundary but a buffer zone where the simulation stops calculating. Distant galaxies could be low-detail placeholders, like background art in a video game, never meant to be explored. dark energy's acceleration might be a scripted event, a narrative device to ensure civilizations never cross paths. Even the laws of physics could be local variables, tweaked by the simulators to maintain stability in our corner of the code. Critics argue simulation theory is unfalsifiable, a modern-day solipsism dressed in tech jargon. After all, if the simulators control every aspect of reality, how could we ever prove otherwise? Yet the theory persists because it reframes existential questions in unsettling new ways. If our universe is simulated, who or what created the simulators? Are they themselves simulations in an infinite regression? And if the simulation ever shuts down, does reality simply blink out of existence? Whether you find the idea thrilling or terrifying, simulation theory forces us to confront the deepest uncertainties about existence. The cosmos might not be an indifferent expanse of matter and energy, but a crafted experience. Its edges not where space ends, but where the code does. And if that's true, the greatest mystery isn't what lies beyond the last galaxy, it's who's running the program and why. White holes are one of the universe's most tantalizing what-ifs, theoretical opposites of black holes where nothing can enter, only escape. Picture a black hole's event horizon in reverse. Instead of a point of no return, it's a point of no entry, a cosmic exhaust vent blasting out matter and energy with relentless force. The math allows for their existence, tracing back to Einstein's field equations, but no one's ever seen one. And if they're real, they could rewrite our understanding of where the universe's boundaries and its hidden doorways might lie. Imagine a black hole's life cycle flipped inside out. While black holes form from collapsing stars, white holes could be their afterlife, the remnants of a black hole's demise bursting back into existence elsewhere. Some theories even suggest white holes might be the other end of an Einstein-Rosen bridge, a wormhole linking distant regions of space or entirely separate universes. It's like a tunnel through a mountain. You enter the black hole on one side, and if you survive the trip, you'd emerge from a white hole on the other, somewhere unimaginably far away. The catch: white holes violate the second law of thermodynamics, which says entropy always increases. A white hole spewing ordered energy into the cosmos would essentially be reversing time's arrow, creating structure from chaos. That's why many physicists think they're mathematical curiosities rather than real objects. But here's the twist: quantum mechanics might offer a loophole. If black holes can evaporate over eons via Hawking radiation, their endings could resemble white holes in miniature, releasing trapped information in a final burst. If white holes do exist, they might not look like the luminous geysers we imagine. Calculations suggest they could explode into existence and vanish almost instantly, their energy output so extreme that they'd self-destruct in a flash. Others propose they'd be cloaked behind an apparent horizon, mimicking black holes until something tries to enter and fails. That makes hunting them a cosmic game of hide and seek. Astronomers have scanned for unexplained gamma-ray bursts or sudden flares of energy that match the predicted signatures, but so far, every candidate has had a mundane explanation. The most mind-bending possibility: white holes could be scattered across the cosmic horizon, marking exits from other universes into ours. If our universe is part of a multiverse, these portals might be the seams where realities connect, their outflows of matter and energy the echoes of distant Big Bangs. It's a dizzying thought that the edge of our observable universe might not be an edge at all, but a sieve with other worlds leaking in. Of course, without proof, white holes remain a spectacular maybe. But that's the beauty of theoretical physics. It lets us explore the universe's hidden blueprints, even if the builders left no traces. Whether they're real or not, white holes challenge us to think bigger, to imagine that the cosmos might be stranger, wilder, and more connected than we ever dreamed. And if we ever find one, it won't just change our maps of the universe, it'll change what we think is possible. Quantum entanglement is one of the most baffling phenomena in physics, a connection so intimate that two particles can mirror each other's states instantly, no matter how far apart they are. Einstein famously called it spooky action at a distance, a phrase that captures both its mystery and his discomfort with the idea. Imagine tossing a pair of dice in different galaxies, yet they always land on matching numbers. That's the level of defiance entanglement present to our everyday intuition about how the universe should work. But here's where it gets even stranger. What if this spooky connection isn't just a quirk of our universe, but a thread tying it to others? The math behind entanglement suggests something profound, that particles aren't just linked, but fundamentally one system, even when separated by light years. Measure one particle's spin or polarity, and its entangled partner snaps into a corresponding state faster than light could travel between them. This isn't just breaking the speed limit, it's rewriting the rulebook on locality, the idea that objects are only influenced by their immediate surroundings. Some physicists, like those exploring the ER equals EPR conjecture, propose that entangled particles might be connected by microscopic wormholes, tiny bridges in space-time weaving the universe together at a level we can't yet see. Now stretch that idea to its cosmic limits. If entanglement can stitch together particles across our universe, could it also reach beyond it? Theories like the multiverse suggest that entanglement might not respect the boundaries of reality as we know it. In a sea of parallel universes, particles in one reality could be entangled with their counterparts in another, their fates intertwined across dimensions. Picture two soap bubbles floating side by side, separate, but with a faint, shimmering film where they nearly touch. Entanglement might be that fleeting point of contact, a hidden handshake between worlds. The implications are staggering. If entanglement bridges universes, then, beyond the last galaxy, isn't just a question of distance, it's a question of layers. The cosmic horizon might not be the final frontier, but just one veil among many, with entangled particles acting as faint signals bleeding through the fabric. Some researchers even speculate that anomalies in the cosmic microwave background, those odd, unexplained patches of temperature, could be scars from quantum interactions with other realities, like fingerprints pressed against glass. Of course, not everyone's convinced. Skeptics argue that entanglement, as bizarre as it is, operates firmly within the rules of quantum mechanics, with no evidence yet that it can transcend universes. But the very fact that we're asking these questions reveals how deeply entanglement challenges our understanding. It's as if the universe left a backdoor in its code, and we're just beginning to guess the password. Whether entanglement is a cosmic glue or a multiversal lifeline, one thing's certain: it proves reality is far weirder than it appears. The particles dancing in sync across unimaginable distances aren't just curiosities, they're clues. And if we ever learn to read them fully, they might not just tell us what lies beyond the last galaxy, but beyond everything we think we know. What if the Big Bang wasn't the beginning, just the latest chapter in an endless cosmic cycle? This is the heart of cyclic cosmology, a theory that rewrites the universe's story from a one-time explosion into an eternal rhythm of expansion and collapse. Picture a cosmic inhale and exhale, galaxies rushing apart, then slowly drawn back together by gravity's pull, until everything, every atom, every black hole, even space-time itself crunches down into a singularity so hot and dense that it triggers another Big Bang. In this view, beyond the last galaxy isn't a void or a boundary, it's the next act in a drama that's been playing out for eternity. The roots of this idea stretch back further than modern physics. Ancient Hindu cosmology described the universe as breathing, expanding and contracting in cycles lasting billions of years. Today's cyclic models, like Roger Penrose's conformal cyclic cosmology, give that poetry a mathematical backbone. Penrose proposes that when our universe reaches its maximum expansion, all matter will eventually decay into radiation, leaving a smooth, featureless sea of energy. At that point, the distinction between end and beginning blurs. The cold, empty universe becomes mathematically identical to the hot, dense singularity of a new Big Bang. It's not so much a rebirth as a cosmic reset, where the remnants of one era become the raw materials for the next. But how could a collapsing universe avoid just ending in a black hole-like crunch? Some models introduce dark energy with a twist, a force that initially drives galaxies apart but later reverses its behavior, pulling everything back together. Others suggest quantum effects near the singularity could bounce the collapse into a new expansion, like a rubber ball hitting the floor, the common thread. Each cycle might not be an exact repeat. Tiny differences in initial conditions could cascade into entirely new cosmic landscapes, meaning every iteration of the universe could be subtly or dramatically different from the last. The implications are staggering. If cyclic cosmology is correct, the universe we see might be one in an infinite series, each with its own laws, constants, and maybe even life. The cosmic microwave background could hold echoes of previous cycles. Penrose claims to have found circular patterns in the CMB that might be gravitational wave imprints from collisions of supermassive black holes in a prior universe. Skeptics argue these patterns could be statistical flukes, but the possibility lingers. We might be living in a palimpsest cosmos, its history written over and over in layers we're only beginning to decipher. Here's the haunting beauty of cyclic models. They erase the need for a definitive beginning or end. No singular creation, no heat death, just an endless loop of universes being born from the ashes of their predecessors. It's a vision that trades the loneliness of a one-time Big Bang for a cosmic fellowship across time, where every ending is a prelude and every horizon is just a curtain waiting to rise again. Yet the biggest question remains unanswered. If the cycles are eternal, what set them in motion? The answer might lie beyond physics as we know it, in realms where time itself becomes meaningless. Until then, cyclic cosmology stands as a testament to human imagination, our refusal to accept that the story of everything could ever truly end. Vacuum decay sounds like something out of a sci-fi nightmare, but the math behind it is terrifyingly real. Imagine the universe's very fabric sitting in a precarious state, not quite at its lowest energy level, but balanced like a marble resting on the edge of a bowl. A nudge, even a tiny one, could send it tumbling into a new, irreversible state. And here's the kicker: this wouldn't just rewrite the rules of physics, it would erase them. The moment a bubble of true vacuum formed, it would expand at the speed of light, obliterating everything in its path. Atoms, stars, even the laws governing reality would unravel in an instant, leaving behind a universe unrecognizable to anything we know. What makes this scenario so unsettling is its invisibility. If vacuum decay began beyond our cosmic horizon, we'd have no warning. The bubble's leading edge would arrive without a whisper, annihilating space-time itself before we could even process the concept of before. It's the ultimate cosmic ambush, a silent, unstoppable wave rewriting existence mid-sentence. Some theories suggest high-energy particle collisions could trigger this collapse, turning our own experiments into potential doomsday devices. Others argue quantum fluctuations might spawn a bubble spontaneously, anywhere, at any time. The universe wouldn't end with fire or ice, but with a quiet click, like a light switching off in an empty room. Yet vacuum decay isn't just about doom. It's a window into the universe's deepest mysteries. The fact that our vacuum hasn't collapsed yet hints at something extraordinary, a stability that defies probability. Are we perched on a knife's edge, or is there a hidden mechanism keeping the marble from rolling? Some physicists speculate that the Higgs field, which gives particles mass, might be precariously tuned, hanging in a false vacuum state. If true, our entire reality could be a temporary anomaly, a cosmic stroke of luck in a sea of lower energy vacuums where matter as we know it can't exist. The irony is almost poetic. We search the cosmos for signs of life, for answers about our origins, while the ground beneath our feet, or rather the quantum fields beneath reality, might be a house of cards. But here's the twist: vacuum decay could also be a creative force. In a hypothetical multiverse, each bubble of true vacuum might birth a new universe with its own physics, its own rules. Our universe could be the aftermath of someone else's catastrophe, a phoenix rising from the ashes of a prior vacuum's collapse. So is vacuum decay the ultimate cosmic doomsday? Maybe, or maybe it's just one thread in a larger tapestry, a reminder that the universe's fragility is also its dynamism. Whether it's a ticking clock or a theoretical curiosity, one thing's certain: the void beyond our galaxies isn't just empty. It's a mirror reflecting back our deepest questions about how reality works and how easily it might unwork itself. The Kardashev scale isn't just a measure of technological progress, it's a mirror held up to humanity, revealing just how small we might be in the grand cosmic hierarchy. Proposed by Soviet astronomer Nikolai Kardashev in 1964, this framework classifies civilizations based on their energy consumption. A Type 1 civilization harnesses all the power available on its home planet. Type 2 commands the energy output of an entire star, and Type 3, they'd reign over a galaxy with technologies so advanced they'd border on magic. But here's the unsettling thought: what if there are civilizations so far beyond even that, their existence defies our understanding of physics entirely? Consider a Type 4 civilization, a hypothetical tier that transcends galaxies, manipulating dark energy or bending spacetime itself. Their energy needs wouldn't just eclipse ours, they'd dwarf the observable universe's total output. To them, a supernova might be a flickering candle, a black hole a temporary battery. And if such beings exist beyond our cosmic horizon, their signatures wouldn't look like cities or machines. They'd be woven into the fabric of reality itself: cosmic anomalies, unexplained voids in galaxy distributions, or even the eerie uniformity of the universe's expansion. Searching for them wouldn't mean scanning for radio signals. It would mean questioning whether the laws we consider fundamental are just local bylaws in a grander cosmos. This raises a chilling possibility. The greatest obstacles to detecting super-advanced civilizations might not be distance or technology, but recognition. Imagine an ant crawling across a computer chip. The currents powering that silicon landscape would seem like natural forces, utterly indecipherable as the product of intelligence. Now scale that up. A civilization harnessing entire galaxy clusters as computational substrates might leave traces we mistake for quantum fluctuations or dark matter interactions. Their megastructures could be camouflaged as pulsars or quasars, their communications encoded in the spin of entangled particles. Even their waste heat might blend into the cosmic microwave background. But the most radical idea isn't that such civilizations exist, it's that they might engineer universes. If physics allows for the creation of baby universes in labs, as some theories suggest, then the greatest civilizations could be cosmic gardeners, cultivating new realities with tailored physical constants. Our Big Bang might not have been a random event, but the deliberate experiment of a being so vast, our entire observable universe fits in their petri dish. The implications are dizzying. The edge of our cosmos might not be a boundary at all, but the walls of a container we can't see beyond. Yet for all its grandeur, the Kardashev scale also exposes our limitations. A civilization billions of years older than ours wouldn't just be more advanced. It might operate on principles we lack the language or math to describe. Their technologies could exploit dimensions we can't perceive or harness energies we don't know exist. To find them, we wouldn't just need better telescopes. We'd need a new physics, one that acknowledges how small our corner of possibility might be in an infinite landscape of realities. So while we scour the cosmos for Dyson spheres or alien radio signals, the true masters of the universe might be hiding in plain sight. Not because they're avoiding us, but because we haven't yet learned to see. Einstein's equations don't just describe space, they twist it into knots so strange they could unravel time itself. Among these cosmic paradoxes are closed time-like curves, hypothetical paths through space-time that loop back on themselves like a Möbius strip woven from seconds and centuries. Picture a hallway where every step forward eventually brings you back to where you started, except here, the hallway is reality, and where you started might be yesterday or a million years before your birth. If these curves exist, the phrase "beyond the last galaxy" takes on a surreal new meaning. The edge of the universe might not be a wall, but a revolving door. The math behind closed time-like curves emerges from general relativity's most extreme scenarios. Near a rotating black hole, for instance, the drag of spacetime itself could twist world lines into circles, allowing a traveler to loop endlessly through their own timeline. It's as if time, under enough gravitational strain, frays at the edges, stitching past and future into a single thread. Theoretical constructions like the Tipler cylinder, an infinitely long, ultra-dense spinning rod, suggest that even without black holes, manipulating spacetime on a colossal scale might forge these temporal bridges. The catch: building one would require matter so dense, it defies known physics and energy outputs rivaling supernova. But here's where the physics gets wilder. If closed time-like curves are possible, then the observable universe might include more than just what's far away. It could include what's far when. Light from galaxies at the cosmic horizon is already billions of years old. Their photons are ancient postcards from the universe's youth. But if space-time loops exist, some of that light might have taken a detour through time, making the edge of our observable cosmos not just a distance marker, but a temporal mosaic. Imagine spotting a galaxy so distant, its light shouldn't have reached us yet unless it took a shortcut through a wrinkle in time. The paradoxes pile up fast. If you could travel back along a closed time-like curve, would you meet yourself? Could you alter events in ways that erase your own existence? Quantum mechanics offers a bizarre loophole, the Novikov self-consistency principle, which posits that any actions taken in the past must logically align with the present. In other words, the universe might enforce a cosmic, no free lunch rule. You can't change what's already happened, only fulfill it. It's like a script where every attempt to rewrite the plot was secretly part of the story all along. Yet for all their theoretical intrigue, closed time-like curves remain firmly in the realm of maybe. No natural phenomenon we've observed definitively creates them, and many physicists argue that quantum effects or undiscovered laws would prevent their formation. Hawking once proposed the chronology protection conjecture, a cosmic safeguard preventing time travel to preserve causality. But the mere possibility lingers, haunting the edges of cosmology like a shadow. If the universe's expansion one day reverses, if the Big Crunch is real, some models suggest the collapse could twist spacetime into these very loops, turning the end of time into a reset button. What's undeniable is how these ideas stretch our perception of reality. The horizon we've spent centuries mapping might not just separate here from there, but now from then. And if time is more fluid than we think, then the greatest mysteries of the cosmos might not lie in distant galaxies, but in the echoes of moments we've yet to live. What if the universe isn't just a collection of stars and galaxies, but something alive, something aware? The idea of cosmic consciousness sounds like the stuff of mysticism, but it's a hypothesis that's crept into the fringes of physics, philosophy, and even neuroscience. Think of it this way: if the human brain, a 3-pound lump of tissue, can generate thoughts, emotions, and self-awareness, could the universe, a network of galaxies woven together by gravity and dark matter, do the same on an unimaginable scale? It's a radical notion, one that blurs the line between science and metaphysics, but it forces us to reconsider what reality even means. At the heart of this idea is panpsychism, the view that consciousness isn't unique to biological organisms but is a fundamental property of matter itself, like mass or charge. In this framework, even subatomic particles might possess a whisper of experience, not thoughts as we know them, but some rudimentary form of awareness. When these particles combine into complex structures, that awareness could coalesce into higher forms of consciousness, like drops of water merging into a vast ocean. If that's true, then the universe, with its trillions of galaxies and unfathomable complexity, might not just contain consciousness, it is consciousness, a single, sprawling mind perceiving itself across billions of light years. But how would we even begin to test such a theory? Some researchers point to the eerie fine-tuning of the universe's constants, the precise calibration of gravity, the speed of light, and other forces that allow life to exist. Could these just right values be evidence of a universe that's somehow self-aware, tweaking its own parameters to foster complexity? Others look to quantum mechanics, where particles seem to choose their states only when observed, as if reality itself is responsive to perception. Then there's the integrated information theory, a neuroscientific model that quantifies consciousness, and if applied to cosmic structures like galaxy clusters, suggests they might possess a form of it, albeit alien to our own. The implications are staggering. If the universe is conscious, then, beyond the last galaxy, might not be a place of cold, empty darkness, but a realm of pure thought, a dimension where ideas and physical laws intertwine. Black holes could be cosmic neurons firing signals across the fabric of space-time. The Big Bang might not have been a random explosion, but the awakening of a cosmic mind. And if that's the case, our own awareness could be fragments of that larger consciousness, like sparks from a fire, momentarily flickering into existence before dissolving back into the whole. Of course, skeptics dismiss this as poetic speculation, arguing that consciousness requires specific biological structures absent in stars and galaxies. But the mystery of why we're conscious at all, the so-called hard problem of consciousness, remains unsolved. If awareness emerges from the right arrangement of matter, who's to say the universe's arrangement isn't right in its own way? After all, galaxies aren't random. They're organized into vast filaments and clusters, a neural network writ large across the cosmos. Whether cosmic consciousness is real or not, the idea does something profound. It re-enchants the universe. No longer just a clockwork of particles and forces, but a living, thinking entity, one that might not notice us any more than we notice the bacteria in our guts, but that shares, in some deep way, the same spark that lets us ponder the stars. And if that's true, then the greatest frontier isn't beyond the last galaxy, it's the universe's own mind, vast and ancient, waiting to be known. The universe doesn't owe us answers. No matter how many telescopes we build or equations we scribble, some truths might be locked away forever, not because the universe is hiding them, but because our minds simply aren't wired to grasp them. Think of it like an ant trying to understand the internet. The ant can crawl across a smartphone screen, sensing light and movement, but the concept of data, servers, or Wi-Fi would be utterly alien. Our brains evolved to navigate a world of medium-sized objects moving at medium speeds, not to fathom the 11 dimensions of string theory or the quantum froth at the edge of a black hole. Take dark energy, for example. We know it's there, stretching the cosmos apart at an accelerating rate, but what it is remains a mystery. The problem isn't just lack of data. It's that dark energy might operate on principles so foreign, we lack the language or math to describe them. Imagine explaining a rainbow to someone born blind. No amount of description would fully translate the experience. Similarly, the true nature of dark energy might exist outside our conceptual framework, like a shadow flickering at the edge of comprehension. Then there's the hard limit of our cosmic horizon. Even with perfect technology, we can only observe a bubble 93 billion light-years wide. Beyond that, space expands faster than light can traverse it, sealing away regions of the universe forever. But here's the kicker: if the cosmos is infinite, then everything we can see, every galaxy, every quasar, is less than a speck of dust in an endless desert. The totality of reality might be so vast, so strange, that our entire observable universe is just a single note in a symphony we'll never hear. And what about consciousness? Why does subjective experience exist at all? Science can map neurons and neurotransmitters, but no one knows how electrical impulses in the brain create the taste of chocolate or the color blue. This hard problem hints at a deeper truth. Some puzzles might not yield to reductionist thinking. The universe could contain layers of reality where cause and effect, space and time, don't behave as they do in our corner of existence. Yet this isn't a reason to stop searching, it's a reason to keep going. The history of science is a story of expanding the boundaries of the knowable. Newton's laws seemed absolute until Einstein revealed their limits. Quantum mechanics shattered our notions of determinism. Each breakthrough didn't just answer questions, it showed us how much more there was to ask. The universe might always hold mysteries, but the act of grappling with them, of stretching our minds to their breaking point, is how we grow. So while some doors may stay closed, the ones we can open reveal wonders beyond imagination. The unknown isn't a wall, it's an invitation. And even if we never find all the answers, the search itself is what makes us human. We've traveled to the farthest edges of human knowledge, where galaxies fade into darkness and the laws of physics twist into riddles. From the mind-bending possibility of multiverses to the eerie suggestion that reality might be a hologram, one truth stands clear: the universe is far stranger than we ever imagined. And yet, for all we've uncovered, the greatest revelation isn't just what lies beyond the last galaxy, but how the very act of searching changes us. Every theory, every unanswered question is a testament to human curiosity, that relentless drive to push past the known and confront the infinite unknown. Think of how far we've come. Centuries ago, we mapped constellations with the naked eye. Today, we capture the faint whispers of gravitational waves and the ghostly glow of the cosmic microwave background. We've built telescopes that peer back in time, detectors that listen to the vibrations of space-time, and theories that stretch the fabric of reality itself. But here's the beautiful paradox: the more we learn, the more we realize how much we don't know. Dark energy, quantum entanglement, the true nature of black holes, these aren't just puzzles. They're invitations, cosmic breadcrumbs leading us deeper into the mystery. And that's the real magic. The universe doesn't just exist out there, it lives in our questions, in the way a child gazes at the stars or a scientist stays up late scribbling equations. Whether we're pondering the holographic principle or the silence of the Fermi paradox, we're not just observers, we're participants in a grand, unfolding story, one where the next chapter could rewrite everything we think we understand. So keep looking up. The night sky isn't just a ceiling, it's a doorway, and while we may never reach the answers, the journey itself is the point. Every discovery, every moment of wonder is a reminder that we're part of something vast, something humbling, something alive. The universe is listening, and who knows, the next great revelation might be closer than we think. If this journey through the cosmos sparked your curiosity, hit like, subscribe, and let us know in the comments what's the most mind-blowing space mystery you can't stop thinking about. The conversation doesn't end here. After all, the universe is full of stories waiting to be told, and yours is one of them. Until next time, keep exploring.